Morning, all of you, and let's solve this beautiful piece. And this will give you learning about permutation combination, binomial theorem, how to use and how to think about these results, and how not to panic whenever you see a very tough problems. Okay. Usually, definitely, J Advanced will not club all the three part into one single problem. That will be too much for this. But the idea is to give you an exposure of how to usually think whenever you see these kind of tough problem in general and especially binomial sequences in particular. So as you can see, we have some factorials over here which gives glimpse of permutation combinations or binomial theorem. Then we have some sigma, which is definitely feeling of sequence in series, maybe telescopic as well, who knows. Then we have limit also, n tends to infinity. So either it will be integration fragrance coming because maybe it's a riemann sum, or probably it can also be done directly by sandwich theorem or some other tools of simply evaluation of limits. So let's see how to go about this. Clearly f of n, g of n has to be evaluated to find the last and third stage of the problem for limit n tends to infinity. यहाँ पे all this mnk they are positive integers until stated otherwise. In fact k, so they are whole numbers as well because k is starting from 0 to 1. Okay, so let's go about it. So first what I'll do is we'll decode this term. Now just by looking at fn it feels very dramatic, but if you keep a watch on what exactly these terms are inside, so probably you can get a hint of dearrangement from here, right? Because these things gives a feeling. Let's say if I keep m equals 3, and that's always wise way to start a problem to get a feel and hang of the ideas involved. So it will give 3 factorial minus 1 to the power 0, which is 1 by 0 factorial. Then we have minus 1 by 1 factorial plus 1 by 2 factorial and minus 1 by 3 factorial, right? And if you evaluate, it simply turns out to be 6 into 1 by 2 minus 1 by 6, and it's not difficult to see. So we have 3 minus 1, which is 2, and which is precisely dearrangement of 3 objects. Okay, so before I go and convince ourselves, I'll give you a quick proof of why this represents dearrangement of 3 distinct objects. So here it was quite easy for case 3 because let's say if we have ABC. Now we want 3 objects to be placed such that none of them is in its original position. So I am telling ABC as the original position. So let's say we'll have 6 possible combinations: ACB or BCA, BAC, we'll have CAB or CB. Now of course first is gone because A occupies the same position. In the second it's possible. Third is gone because C is still in the same position as C in the beginning. Fourth still works, and fifth is gone because B is not in the, should not be in the same position. So hence we have for 3 objects, the arrangement gives 2. Now this you can prove from inclusion of principle of inclusion exclusion. So let's say I'm first showing you particularly for 3. So let's say we have 3 positions of object ABC, and I represent set A. This is our entire universe. So let's say set A is represented by the set where it's a 3-digit numbers or 3 letters word where A is in its original position, right? So set A represents A is in its original position, and B and C can be anything. Similarly, set B represents B is in its original position, and I have not told anything about A and C. Set C represents C to be in original position, right? So with this notation, I can clearly apply principle of inclusion exclusion, and the number of elements in A union B union C will be at least one of them will be in original position. Total will be n of A, number of element in A, which is if A is in the original position, the other 2 can go into factorial ways, plus in B and C, so exactly same, so 3 into 2 factorial, minus number of elements in A intersection B. Since A intersection B, B intersection C, and C intersection A will be same by symmetricity. So when A and B is in the same position, it means now we want A and B to be in same position, so we have only one choice, so it's minus 1 minus 1 minus 1. And now we'll add when all three are in the same position, so that's still 1. So that will give you we have 6 minus 2, which is 4. Now total number of arrangement, because these A union B union C represents all possibilities where at least one of them is in the same position. But dearrangement means we want this white region, so we want A union B union C bar. So now the total number of possibilities for these three objects will be 3 factorials. Okay, so 6 is total possibilities, which is this entire universe, and out of that, if I'll take away A union U, B union C, which is 6 minus 4, so I'll get 2 as the answer for dearrangement of 3 objects. Of course, in general, you can do it for 4 also, and hence we can generalize for 1. So let's do it for 4. So for 4, we'll have number of elements in A union B union C union D, and I'm defining exactly now D. So we'll have one more box over here, and D is the number of arrangement in which D is in the original configurations, which is at the last place. So now it is number of elements in A plus B plus C plus D. So since because of symmetricity I am writing it 4 times, minus A union B, so 4C2, which will be 6 times taken A union B, plus we'll have again A intersection B intersection C, which is over counted, it's a principle of exclusion, and we'll have 4 times here, and then minus all 4. And that's easy to count. 4 into when exactly, let's say A is in its first position, and same goes with B and C and D, hence I'm writing 4 times of this by symmetricity argument. So we'll have 4 into 3 factorial, which is 6, minus 6 into when 2 of them is in same position, let's say A and B is in same position, so remaining can go with 2 factorial. 3 of them in same position, 4th has to be the same one, and all of them in position is 1. So now we'll get 24 minus 12 plus 3, so which gives you 27 minus 12, and that goes to 50. Right? Now, of course, I'm interested in A union B union C union D conjugate. So none of them should be in its original places. So that will be 4 factorial minus 15. So it simply goes to 24 minus 15, which is 9. So this is a very elegant way of proving this dearrangement formula. So by now you must have been convinced like m factorial into this will give the answer, because in general, let's say if you have m set, so total number of objects will be m factorial minus when we want exactly one of them to be in its correct position. So out of m, I'll choose 1, and for one of them to be in correct position, we'll have m minus 1 factorial ways. And similarly minus, now we want 2 of them to be in correct positions, m minus 2 factorial ways, plus 3 of them in correct position, m minus 3 factorial into m plus 3, and so on and so forth till we die, right? And from here you can easily evaluate and check like this is same as m factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, and so on and so forth, right? So this is a total way of dearranging m distinct objects. So I hope it is very clear from the principle of inclusion and exclusion. Hence first part of the first problem is done, and I can tell is nothing but dearrangement of an object. Now let's decode further. What does NCM DM represents? So again, let's take particular example. Let's say we have 5, n is 5 and m is 2. So what does 5C2 D of 2 represents? It means out of 5 distinct objects, 1, 2, 3, 4, 5, I am first selecting any 2 of them. So let's say if I select our object O1 and O2, and then I am dearranging them. So dearrangement means either O1 and O2 will be definitely will not be in this position. So the only way of dearranging O1 O2 will be O2 will be their first place and then 1 as second place. Right? So this is precisely what it means. Or I could have selected O3 O4 also, and dearrangement is O4 and O4. So now we want sum of m equal to 1 to n NCM D of m. So that decodes as, so let me write it further over here. So that decodes at NC1 rearrangement of 1 plus NC2 rearrangement of 2 plus NC3 rearrangement of 3 and so on and so forth. Let's say NC n and rearrangement of n. Now let's decode what exactly this means, which is basically f of n over here, right? So if I'll decode first, so I have, let's say, n distinct object O1, O2 till On. So out of this, I want to select any one of them, and in how many ways they can be rearranged into one position so that O1 does not go to its original position. So clearly it's 0. This will give 0, right? There is no way. Now what does NC2D2 means? That I have told. So we can select O1, O2 and then rearrange. So the arrangement means we'll have O2 and O1 arrangement over here corresponding to this, right? Similarly, if I select O2, O5, let's say, so the only arrangement will be O5, O2. So it's count for all those arrangements where none of them, O2, O1, is not in the original position. Now what about NC3D3? So it selects 3 objects, let's say O1, O2, O3, and it arranges, it maps this to O2, O3, O1 case, or O3, O1 and O2 case, because the arrangement of 3 will do, right? Similarly, NC and the arrangement of n, it takes all of them and it dearranges. So there will be many cases, in fact, exactly the arrangement of n. Now we can also look this from the other perspective, because what fundamentally we are doing is, you can imagine if I directly arrange this n objects, so there will be n factorial arrangement. For example, we'll have O1, O3, then O2, and everything is in its original place. So basically I can decode let's say O2, O5 as an arrangement where O2 is not going to its original place and O5 is not going to the original place, right? So instead of O1, O5, here we have O5, O1, and the remaining string is still the same. Similarly, I can decode NC3. So the number of ways of getting NC3D3 is same as when those 3 items are not going to original place and the remaining is still in the place. So this entire arrangement is automatically counting entire n factorial, except one case where nothing goes to, when everything goes to their original position. So that is not being counted over here, right? So it's basically this count everything except one. So one case represents when it's a case when everything goes to its original position. That's not been taken care of. Because in any of the arrangement, either exactly one of them will be in the original position, or 2 of them will be in original position, or 3 of them will not be on original position, or 4 of them will not be in original position, or none of them will be in original position. That's the only possibility in the entire universe. So with that perception, I can tell the first term is going to be n factorial minus 1, and since we have plus 1, so it's cancelled and fn becomes n factorial. So this was pure combinatorics logic over here, where I have first proved the rearrangement formulas. I gave you the field for n equals 3 and 4, then we generalized it using principle of inclusion and exclusion naturally, and finally we have shown the great answer for f of n is nothing but simply n factorial. Now let's move to Gn calculations, and I'll do it over here. Okay, fine. So let's move to this Gn calculation over here. Now again, there doesn't seem any nicer way to give the combinatorics logic as of now, because it can be given but it will be tougher. And since we have 3 distinct binomial terms, so we expect to multiply 3 different expansion, right, using convolution or using this series expansion and equating the coefficients. So that seems tougher over here. So the better method is, in this kind of problem, when we have more than 2 binomial coefficient, is directly go for multiplication. And a similar kind of problem has been already asked in JEE Advanced 2021. In this similar style, I created this. So let's see how to decode. So we'll get 2n factorial divided by 2k factorial, I'm blindly decoding it. 2n minus 2k factorial. Second term is 2n minus 2k factorial, NCR definition, and it will give n minus k factorial to n minus k factorial. Next term is 2k factorial or k factorial into k factorial. Now let's see which quantity gets cancelled out. So straight away this gets killed off. We have 2k factorial getting killed off with 2k factorial. And now I can see n minus k factorial and k factorial. So that demands their summation as a motivation of NCR. So n minus k plus k is n. So I'm tempted to bring n factorial into picture. Similarly, the other guy also demands n factorial. So I'm tempted to put another n factorial. Hence I have to divide by 2n factorials. And now our life seems good because 2n factorial is being adjusted with this n factorial, that in the format of 2ncn. And this n factorial together with n minus k and k, these three guys, again sets very nicely, which is nck, and we have one more nck over here, which is coming out of these three guys, right? So now the sum becomes really cool because what you can see immediately is 2ncn I can plug out because what is changing over here is k. So I can happily plug out 2ncn, which happens with most of the JEE problems. And now we have k equals 0 to n, nck times nck. And now here is a great idea. Either you can use series concepts or you can use a story making of combinatorics, or here I am using van der Monde's identity, V identity. So for those who have not done, please refer to van der Monde's identity because it's very crucial for JEE problem solving. In fact, your 40 to 50% of mains and advanced problems is based on this. What I'll do is nck I can write as ncn minus k, and now I can see the hallmark of van der Monde's because n and n is fixed, upper index is fixed, and lower index sum is n. This you can give combinatorics argument also. Let's say we have 2n students in a class, and we have exactly n boys and n girls. So the number of ways of selecting is 2ncn, n students from the class. You can also think in this way: first you select 0 girls, these are let's say girls and boys, and then you select all n boys, or you can select 1 girl or n minus 1 boy, and so on and so forth. That's precisely this summation, right? And hence I can directly write 2ncn, sum of upper index, which is 2n, by sum of lower index, so k plus n minus k gives n. And very interestingly, you see what we got is 2ncn whole square. Right? So the second expression evaluates to 2ncn whole square. Well, so this is what we got for the second expression. Now it's final turn to evaluate this limit. So what does root gn look like is 2ncn. Fn is already n factorial divided by n ka power n whole to the power 1 by n. Now hold on, before we go, smack it down. So 2ncn into n factorial can be written as 2n factorial over n factorial into n factorial into n factorial. And n factorial gets kicked off, so it's 2n factorial by n factorial. Now we can multiply this till n, and then n plus 1 till n plus n over n factorial. N factorial gets kicked off, and finally we have n plus 1 into n plus 2 till n plus n. So this is one part of the summation which I needed to find. We have to divide by n ka power n and then take 1 by n through it. So let's divide this by n ka power n. So let me do it over here and take whole to the power 1 by n. And I want to evaluate this limit n tends to infinity. Now it's a typical Riemann sum because you can see if I take this limit as L, and since log is continuous in its domain, okay, so if I'll take log function from R positive to R, it's a continuous function, hence I can use ln L equal to 1 by n ln n plus 1 by n plus ln n plus 2 by n and so on till n plus n by n. And it's not difficult to realize. This can be written as 1 by n, and of course limit n tends to infinity, so that I'll be taking at the last. And limit n tends to infinity ln L is same as ln of limit n tends to infinity, right? Because of the continuity postulates. So anyway, this can be written as ln of 1 plus n by n is 1. So 1 by n plus 2 by n, I'm writing r by n. And we can use now famous sigma notation to convert into Leibniz, where r is running from 1 to n, to 2n, right? 2. Let's convert into Riemann integration. So sigma converted into integral with the notation of r by n as x. R equals 1 corresponds to 1 by n as the lower limit, x star, n tends to infinity will go to 0. When r is 2n, so 2n by n goes to 2. So it's ln 1 plus x and 1 by n dx. So now the entire question is just ln of 1 plus x dx. Let's make a substitution of 1 plus x equals t. So that gives me t going from 1 to 3 ln of t dt. And now we have it's t ln t integration by parts minus t value from 1 to 3. So we'll get 3 ln 3 minus 3 minus 1 ln 1 minus 1. So that's 0. We have 3 ln 3 and it will give minus 2. Please do check my calculation. So we have ln 27 minus ln e square. Right? So it's ln 27 by e square. And remember that was ln L. So the final answer to this question after a long patience is 27 over e square. So point was just not to solve the question, but I created it for you so that you can see how we can think for all these different parts. So you can take this as 3 different problems, right, to solve it by yourself. So I hope you must have learned a lot from this problem. Also ideas how to tackle these kind of situations. So the takeaway was, first you put some particular value of m and n to get a feel of the situations. The feel will be felt very easily because of your limited JE syllabus, you can easily see like something familiar would happen. Okay, so then you can connect the logic very nicely. So I hope you are enjoying these lectures, and moreover this is giving you thrill and challenge how to approach the unique problem with these basic tools. If you really liked it, please do like and subscribe so that I can come with more motivation